everyone, this is the last class of this week. What we have been doing is we have been demonstrating the various steps involved in metric method of structural analysis of beam through one example, and the example that we have presently in our hand is this one. Okay. So far what we have done is we calculated we have done the step 5, which is solution for unknown displacements. We calculated the member stiffness matrix, assemble them, and then after assemble, then we applied the boundary conditions and they calculated the nodal load vector and then solved for unknown displacement. And for this, the unknown displacements are 2 u1 and u2, all other displacements are 0 because of the constant, and the values of u1 and u2 is this. This we have already done it in the previous class. Now, today what we do is, today will be the step 5, step 6 we will see how to calculate the support reactions and then member forces. Okay. So, you see, if you recall, this is a very important slide. It says it has a core of the core concept of this entire exercise that we are doing. Now, we have a beam, we identify the different segments first, and then each segments are now divided into, each segments are considered separately. Now, each segments are, now we have a two part. The entire problem is now divided into two part. One part is each segment is considered as fixed beam, and therefore we calculate the fixed end moments, fixed end forces and friction moments, which are called fixed end reactions. Now, by making all the ends are fixed, we essentially constrained all degrees of freedom. So, there is no degrees of freedom in the member. So, only the member is whatever forces we have, that force is due to the externally applied load. Now, then in actual structure, in addition to the external because of the externally applied load, there will be a deformation. In the first part there is no deformation, and the second part we have just only deformation. And in actual structure, what is happening? Both together, right? We have forces and the deformation. So, therefore, whatever reactive force you have, that reaction force will have two contribution. One contribution is from the first part, which is kinematically determinate structure, contribution from that kinematically determinate structure only due to the external load, and then there will be another contribution because of the deformation of the structure. So, total force, total reaction at the support will be not only the total reaction at the support, even the member forces. Total member forces and the reactions will be the contribution from first part plus the contribution from the second part. Now, first part is already we have with us the fixed end actions. We will now concentrate on the second part and then add to the first part to get the support reactions and the member forces. Okay. So, you see, so we have now this is two segments, and so what we have is, so for the fixed end moments, if you recall, these are the fixed end. So what we have is we have for this we have we have fixed end moments, fixed end actions. There will be fixed end actions. Remember, anticlockwise moment and anticlockwise rotation is considered as positive, and there will be a force here. There will be a force here, and similarly we have this and then this, and there will be force here, and there will be force here. So, these are all fixed end actions. We already know what are the fixed end actions for this structure. And then we have just now I mentioned this is for kinematically determinate structure. There is no degrees of freedom, all degrees of freedoms are constrained. Now in addition, now the structure when they deform, because of the deformation there will be some actions at the joints, action at the supports, and suppose these actions are this. Similarly, these actions are this corresponding. So, support reactions will be, total support reactions at any joints will be this plus this. So, if I take this beam, so at fixed end we have force, then moment, and this force is say y a, vertical direction at A, and this is MA, moment at A, and then we have force support reactions at B, suppose this is YB, and then support reactions at C, this is YC. Then MA will be contribution from this plus contribution from this. Okay. Similarly, YA will be contribution from this and contribution from this, and YB will be contribution from this, contribution from this, and then contribution from this. This will be YB, right, and so on. And similarly, contribution from C will be, it will be contribution from this, contribution from this. Okay. So, this is will be the total reactions. Similarly, the member forces we will also see the similar count. Similarly, we can obtain the member forces as well. Okay. So, so fixed end moments already we have. Now, we will see how to get the contribution for the displacement part. Okay. So, this is the displacement, all displacements are, we have just only two non-zero displacement U1 and U2, all other displacements are 0, and values of U1, U2 are this, we already obtained it last class. Okay. Now, if you also remember in the last class we discussed, if P is equal to K into U, if this is the relation, force displacement relation, then that relation can be partitioned depending on the unknown displacement. We can separate unknown displacement and unknown displacement, and similarly we can partition the stiffness matrix and the load vector, and if we do that, this will be we get something like this. And if you recall, this PK are the nodal equivalent load vector, at the joints where displacements are unknown. And if we solve this equation, if we solve Pk is equal to K11 into U plus K12 into UK. If you solve this equation, you get U unknown. UK is 0 and this one is known and this is nodal vector node. If you solve this equation, you get U unknown. Okay. Now, in order to get, now we will use this second equation. Second equation is, you see what we want is, if you recall in the second, if we just now we discussed, we need the contribution. This fixed end contribution already we know, fixed end actions. We need what is the reactions generated due to the deformation, and the deformation, the entire deformations are now are represented by only two non-zero degrees of freedom, one is U1 and U2. So, because of this U1 and U2, what are the reactions generated at this support because of the deformation? Now, that in order to get that, we use the second part of this equation, and the second part of this equation will be this. So, this will be K21 into U unknown, which is now known because we have already determined it, plus K22 and U known, which is anyway 0. Now, this contribution, this gives us the forces, the reactions at the joints because of this, because of the deformation. Okay. Let us find out that. Now, if you recall, our global stiffness matrix was like this, and in this global stiffness matrix, this is how we partition the matrix. This was K11 and then a sub matrix, and this was K12, and this is K21 and this is K22. So, now what we need is, we need this part. Okay. So, we have to compute K21 into U unknown, now which is known, means we have to compute K21 and then U1 U2. Okay. U1 U2 we have already determined the values, and K21 will be this part. This is 4 by 2 matrix and U1 this is 2 by 1 matrix, which gives us the forces at the joint, the reaction at the joint only due to the deformation, which is 4 cross 1. So, 4 unknown joint reactions we get. Okay. Let us do this exercise. Now, so U1 U2 is this. Let us find out what is this. Then K21 into U1 U2, that will be K21 is EI. If you check, this will be minus 0.96 and then minus 0.96 and then 0.96 and this is 0.72. We have 0 here, then 0.24, 0.24 and then 0 and 0.4. Okay. Now, this is for this and then we have U1, U1 is minus 6.25 by EI and then 12.5 by EI. Now, if we this gives us, so if we do this multiplication, this gives us minus 6, this EI and this EI gets cancelled, minus 6, 3, then 3 and then 5. Okay. So, therefore, total reactions will be now, suppose these reactions are in this case. So, these reactions will be suppose here if we draw this beam once again and the reactions are this is R, this is R, this is YB, YA and this is MA and this is YB and this is YC. Okay. We need to calculate now these reactions, but remember when we implement it, we do not the degrees of freedoms or associated forces are not represented as MA, YA, they are represented through some numbers, right. So, the numbers that we used, if you recall, the numbers are the numbers we used is for this it is U2, this is U3, this is third degree, this is direction 3 and this is direction 4 and this is direction 5 and this is direction 6, right. So, what we get is we get this is, so now what we have is we can these total forces will be this plus, in addition to that this plus we have the contribution from the fixed end reactions and that fixed end actions are 0, then 30. You can cross check from the previous class, this is the and then corresponding values will be minus 6 and then 33, then 33 and 30, right. So, what is this? This is associated to degrees of freedom 3 and then degrees of freedom 4, it is associated with direction 3, direction 4, direction 5 and direction 6. So, essentially this is direction 3 is YC and direction 4 is YB and direction 5 is YA and then this is MMA, this is MA. Okay. So, this is the total reactions. Okay. Now, let us check whether the equilibrium conditions are satisfied or not. Reactions wise, total force here is 12 spanning over 5 meters. So, total downward force is 60 kilonewton and then support reactions we have YC plus YB plus YA, YC, YB and YA 33 plus 33 66 minus 66 60. So, equilibrium condition satisfied. This is important to check. See, equilibrium condition has to satisfy because that is the basis of entire all this formulation. But when you numerically implement it, it is good practice to cross check whether numerically the equilibrium being satisfied or not, because that gives a confidence over on your numerical implementation. So, this is how the reactions can be obtained. Okay. Now, similar approach we can follow to find out the member forces. Okay, so member forces will be, we take any member, and then this member will have the member forces in that particular member will be having two contribution, one contribution from the fixed end action and another contribution from the because of the displacement. So, one contribution kinematically determinate structure, no displacement, and the second contribution will be only displacement, no external load. Okay. So, let us do that exercise. So, now we have just now discussed this. Okay. So, let us find out now member forces. Okay. Now, this is how the numbering of the members and joints are done. So, we have two contributions, as I just now said. One, so member forces are what? Member forces is, if we take any arbitrary member for say member number 1, this member number 1, this member number 1. So, in this member we have shear force and bending moment, no axial force. Please recall, please remember, in this formulation the stiffness matrix, while constructing the stiffness matrix we assume there is no axial deformation taking place, and therefore, there is no axial force, only the response we have is the bending moment and shear force. So, we have a bending moment here, and then we also have a bending moment here, and then we have a shear force here, and we have a shear force here. Okay, member forces. So, you see the bending moment and shear force, when I represent their direction is represented as we considered positive and negative in algebraic calculations. Okay, it is, bending moment can also be the sense of bending moment in generally in beam. If you recall, sense of bending moment is either the bending moment is sagging moment or bending moment is hogging moment, right. Now, but when you numerically add them or do the algebraic manipulations between the moments, then the sense that you have to consider is whether it is clockwise or anti-clockwise, not sagging and hogging moment. Okay. So, since our anti-clockwise is considered as positive, that is why this is shown like this. Okay. Now, so suppose let us write it, this is member number 1, this is member number 1. So, suppose this force is Q5 for member number 1, and then this, okay, this is Q5 for member number 1, and similarly this is Q2, this is Q4 for member number 2, for member number 1. So, this is Q4 member number 1, this is Q5, this is Q6 for member number 1. Okay. So, Q6 is the bending moment, Q4 is the bending moment, and Q5 and Q4 are the shear forces. Now, similarly for member 2 will be, we have force, the bending moment and shear force can be shown like this, and then force, and let us call it as this is Q4, this is Q4, but for second member, this is Q2 for second member. Okay. Similarly, this is Q3 for second member, this is Q1 for second member. Okay. Now, so this set is the bending moment shear force for member 1, and this set is bending moment shear force for member 2. Now, what would be Q-6? Q-6 will be contribution from this plus the contribution in the member forces, contribution from due to the deformation. Similarly, all these member forces will be contribution from the fixed end action plus the contribution due to the displacement. Contribution from the fixed end actions already we have. Let us now find out what is the contribution for displacement. Now, in order to do that, what we do is, if you recall, this is member number 1 and it is the stiffness matrix for member number 1. Okay. This is this is for 1, this is 1. Okay. Member number 1. So, this is the corresponding stiffness matrix. So, what we will have is, we have say Q5 member number 1 and then Q6, and then Q4, Q2, Q4 and Q2, this entire thing will be this stiffness matrix K1 into displacement. What are the displacement? Displacement will be U5, then U6, U4 and U2. So, this is the contribution, this part is the contribution from, this part is the contribution due to the displacement, and then in addition to that we have contribution from the fixed end moment, right, contribution from fixed end actions. Now, plus contribution from fixed end actions. Now, for this the fixed end actions are 30, 25. You can check the fixed end moments and then forces minus 25. Okay. Now, we already know that U5, U6, U4 they are 0, U2 is equal to 12.5 by EI. If we substitute that and then this expression, this final will be, it will be 33, then again 30, then 27 and then minus 15. Okay. So, where U2 is equal to 12.5 by EI, and all other U5 is equal to U6 is equal to U4, they are 0. So, K, this matrix is this matrix, these are the degrees of freedom, plus this is the contribution from the fixed end action, and this will be the member force. This will be the member force for member 1. Okay. Now, similar exercise if you do it for member 2, let us do it. Member 2 will be, this is for member 2, and then again is you make it for it is for member 2, this is for member 2, right. And then similarly the member 2 will be, it will be Q okay, use okay, Q4 2 and then Q2 2. The order, this is order because this is how the degrees of freedoms are, this is how the degrees of freedoms are arranged, and this is how, depending on this arrangement, your stiffness matrix is constructed. Okay. And then U3, Q3 2 and then Q1 2, 2 stands for second member. So, it will have contribution for displacement plus contribution from the fixed end action. Displacement contribution will be same, this will be K2 and then we have U4, U2, U3 and then U1. Okay. And plus the displaced contribution from the fixed end moment, and if you recall for this there was no load on this span. So, fixed end actions were 0, all 0. Okay. In this expression we know that U1 is equal to, if you recall, minus 6.25 by EI, and U2 is equal to 12.5 by EI, right, and all other U3 and U4, U3 is equal to U4 is equal to 0. Now, if we substitute this and K2 is equal to this, fixed end actions is this, if you substitute that, the values that we get is 6, then 15, minus 6 and 0. Okay. So, this is the fixed end, this is the member forces for member 2. So, once we have the member forces for member 2, and if you recall how you constructed the bending moment diagram and shear force diagram, we can same way we can follow to construct the bending moment diagram and shear force diagram. So, all the information we need to construct the bending moment diagram, shear force diagram, or bending moment to get the bending moment and shear force at a given point, we have those information. Okay. Now, these informations are obtained through matrix method of structural analysis. Okay. So, this is a very brief, depending on the problems, the dimensions will be different, the scale will be different, but the essence of the steps involved in any problems in beam will be exactly the same. Okay, the similar exercise you can do it for different problems. For larger problems, there are some issues, implementation issues. There are something to be we have to consider. We have to, while the giving the numbers and all. As I said earlier, this will be discussed in detail in week 7th when you talk about various implementations, implementation aspects. Okay, so. Before we close, you see, suppose your flexural rigidity is not constant with the same problem, but if I in the previous example, the EI is constant for all the members, right? But suppose EI is not constant, in one member it is EI, or you may have something like varying EI. So either your geometry is continuously changing along the length. You may have different kinds of such geometry. Okay. So, in this case, suppose for the first it is it is 2 EI and it is EI. 2 EI, either their Young's modulus is the more, or its shape is different, so that the second moment of area is twice the second moment of area, the second one. There may be different reason, but the total effect, net effect is, suppose the EI is 2 EI here and it is EI here. Okay. So, the thing is exactly the same thing, there is no difference at all. Only thing is, you recall this is for any arbitrary member, this is the stiffness matrix, and in this stiffness matrix these are the, in this stiffness matrix, these L, wherever you have L, this L is the length of this member, and EI is the Young's mod, EI is the EI flexural rigidity of this member. But for some member, if you find it is 2 EI, then instead of EI it will be 2 EI, instead of all EIs it will be 2 EI. So, whatever is EI of that particular material, you have to substitute that value here to get the member stiffness matrix for that particular segment. Okay. So, then rest of the thing is exactly same. Once you have the stiffness matrix for all the members, then assemble them to get the global stiffness matrix, apply the boundary conditions, partition the matrices, and then solve for unknown displacements. Once you have unknown displacements, and then next you calculate the joint reactions, joint reactions and member forces. But when you calculate joint reaction and member forces, there will be two contribution, one contribution from the fixed end action, another contribution due to the deformation of the beam. Okay. So, this is the matrix method of structural analysis for beam, and it is demonstrated through an example. I would say very simpler example, because in classroom demonstration we had to take an example where the matrix size is small, degrees of freedoms are less, unknowns are less, so that we can solve them here. But same thing you can, but the same exercise what we have done manually, same exercise you can code, write a program and apply that for a large structure where we have many members and many joints. Okay, but the essence of the steps will remain same. So, I stop here today. Next week we will start the matrix method of structural analysis for frames, for plane frame. You see, you recall in truss problem, the behavior of the trusses, every member is subjected to only axial force, either compression or tension. There is no bending, there is no shear. In case of beam, we have bending moment and shear force, we assume there is no axial force. Now, in case of frame, we have to just combine these two. We have a truss where only axial force, we have a beam where bending moment and shear force. In frame, we have axial forces, we have axial force, we have bending moment, and we have shear forces. So, three forces we have to consider. Therefore, while constructing the degrees of constructing the stiffness matrix, we really do not have to do all the exercise that we have done for truss and beam problem, because we have to just slightly reorient these two stiffness matrices, one for truss and one for beam. We have to combine these two stiffness matrices to get the stiffness matrix for frame element. That exercise we will do in the next week. Okay, I stop here today. See you in the next week. Thank you.